Well, now that we have completed our study of atomic theory, one of the last areas that we had talked about in atomic theory had to do with valence electrons. And valence electrons are the electrons that are available for bonding. They're the outermost electrons, and those outermost electrons are the ones that actually cause interactions and chemical reactions to occur. So how they bond, that's going to be the word that we use to talk about that chemical interaction, impacts the behavior of elements and compounds. So we're going to talk about two common substances just as an example to begin with, and that's going to be graphite. And graphite is all pure carbon, and the carbon kind of forms a shape like a hexagon, and that one is connected to another one, and this is just a simple idea of how carbon as graphite appears. So this is one allotrope of carbon. Another one is going to be diamond, and diamond structurally is a little bit different. We describe it as a tetrahedral, or sometimes it's also described as an octahedral, but one group is attached to another, and so you get this octahedral effect where these carbons are just interconnected, and this is part of what makes diamond such a strong, powerful substance, is the bonding and the interconnectedness. So let me give you a little idea. Just take a look at a web page here that shows the two different substances, both allotropes of carbon. Allotrope is simply an element that occurs in different forms. So for the structure of graphite here, you can see the graphite occurs in these great big sheets. Now there's very weak forces that binds the one sheet of graphite to the other sheet of graphite, and the pressure that you apply on a pencil when you're writing is what's going to cause the graphite to actually rub off onto the paper. Whereas diamond has a structure where there's a great amount of interconnection between the carbon atoms that are in there, and doesn't occur in sheets, and it's extremely hard substance. So both diamond and graphite occur naturally. Diamond is the hardest substance known to man, and graphite is soft and greasy to the touch. High density for diamond, low density for relatively low density for graphite. And you can see some of the other properties here. Diamond does not conduct heat and electricity, but graphite is a good conductor. Why are these two things so different? It only comes down to the fact of their bonding in the molecule. They're both made of pure carbon. So pencil lead, or graphite, is actually used as a lubricant because of its greasy nature for locks. But diamond is one of the hardest substances known to man. So when they build roads and they have to drill through a mountain with these great big machines, they use diamond to do that drilling. And it is used in a lot of industrial cutting operations. Both are just pure carbon, but the difference is in how the carbon atoms are connected, and the technical word bonded to each other. So what this chapter is all about is how molecular bonding and geometry play a huge role in how chemical reactions occur, as well as the physical and chemical properties of substances. So molecular bonding and geometry. So let's continue on, talk about the kinds of bonds. So when we talk about a bond, it takes energy to break bonds. So this is a little opposed to how biology thinks about things. So if we're putting energy into a system, that energy is going to be used to break bonds. And we have, and you don't need to remember this, but there are tables of what is called bond dissociation energy. So breaking bonds puts energy into a system. You get energy out when bonds are formed. And so bonds forming is going to give energy when they form rather than when they break. That's how chemists think of it. Biologists look at it a little bit differently. So we've talked about ionic compounds before, and we'll do some practice once we get in class. I have a worksheet for you, and there are things called ionic bonds, and there are covalent bonds. And we're going to talk about the difference between these two, and this is just a very quick look at it. Ionic bonds are formed between a metal and a nonmetal. And as we learned in our previous chapter, metals love to give away electrons, and nonmetals want to gain electrons. So we talk about a common substance like sodium chloride. Sodium has one valence electron. It's in the first group, the alkali metals. So I'm going to put a little dot next to it to show that it has a valence electron. Chlorine, on the other hand, has 7 valence electrons. It's a halogen right next to the noble gases, and as such, it is a very small atom, and it's small because the protons in the nucleus are attracting the electrons. Well, when sodium and chlorine come close to each other, sodium, a metal, wants to give away its electron. Chlorine, a nonmetal, wants to gain that electron. The result of this is that sodium now has one more proton than electron. Chlorine has one more electron than proton, and sodium becomes a positive 1 ion, chloride becomes a negative 1 ion, and the charges add up to equal 0, and that's important. That's a valid ionic compound when the charges add up to equal 0, and we get sodium chloride. Covalent bonds, so what we call this ionic bond is actually a transfer of electrons. And so transfer of electrons is what causes ionic bonds to form. And there could be more than one electron that transfers, but it only happens between a metal and a nonmetal. Covalent bonds are formed when nonmetals, and there would be 2 nonmetals or more, nonmetals share electrons. So important point, ionic compounds transfer electrons, and nonmetals share electrons in a covalent bond. So let's say we have, let's do something simple like fluorine and fluorine. These are 2 halogens. They each have 7 valence electrons. And I'm going to put those lone electrons right next to each other because they end up forming a bond. So this bond, that is a covalent bond, and the fluorines are sharing electrons. The cool thing is that both fluorines see those bonded electrons as their own, and if we count the little dots around the fluorine and we count the line connecting the 2 fluorine atoms as 2 electrons, each of them has 8 electrons, and that is a complete energy level for S and P orbitals. So there are 2 electrons that would fill the S, and there would be 6 that would fill the P, and that gives us 8 total. And that seems to be a great number for stability for compounds. So just as a reminder, ionic compounds, transfer of electrons creates ions, and those ions give us a formula for an ionic compound. Covalent bonds are formed when 2 or more nonmetals share electrons, and 8 electrons seems to be a magic number. Notice up here for the sodium chloride, when sodium transferred an electron to chlorine, the outermost shell of chlorine now has 8 electrons. Sodium actually went backwards to get enough electrons in order to lose 1 electron to go back to a noble gas configuration. 8 electrons, very similar to what neon has in terms of electron configuration. So there is no bond that occurs, no bond whatsoever between metals. If we mix metals, we get a mixture, and we call that mixture an alloy, okay? So we never talk about metals making a compound. Metals make alloys and not compounds. It is possible to have nonmetals share electrons and form a compound, but metals don't do that same thing. All right, so let's move on and let's do a couple of examples of ionic bonding. You saw before how I combined sodium with chlorine, and I transfer an electron. That produces sodium as a positive 1 ion and chloride as a -1. And by the way, we changed the name of Cl chlorine to chloride when it's an ion, and that gives us a valid compound NaCl. The positive 1 and the -1 charges add up to equal 0. Now, if I did this with strontium, strontium actually has 2 valence electrons, and bromide is not an ion yet, but we're going to make it one, is going to receive an electron from strontium. And when it receives that electron from strontium, it now has its 8, but strontium still has a valence electron left over. So it's going to want another bromide to transfer that second electron to. So as a result of doing that, strontium now has a +2 charge. And I've got 2 Br minuses. And the way that I write that formula is I don't leave the 2 here, but I use it as a subscript. So the formula for that compound would be SrBr2. And strontium +2 charge, and I've got 2 -1 charges, and the -1 charge times 2 is -2, so +2 -2 adds up to equal 0. So this is the actual formula for strontium bromide. For covalent bonding, we're going to take 2 chlorine atoms, and chlorine has 7 valence electrons, and we're going to share because these are both nonmetals. So nonmetals want to share electrons, and we draw a line in between them to show that connection between them. And that connection will allow them to form the molecule that we call chlorine. It's diatomic, and it has a bonding pair of electrons and 3 non-bondings on each chlorine. So this is why chlorine is a diatomic, and the formula for that is Cl2. It's an element, but it occurs as molecules. So there are two basic types of bonding. The electron transfer, which is for ionic compounds, and electron sharing. And electron sharing is for covalent compounds. So in a perfect world, we say that ionic bonding is complete electron transfer. It creates ions. Covalent bonding is electron sharing. And literally there are two subcategories. If we have pure covalent, then we have equal sharing. So when you have two atoms that are identical to each other, and here's an interesting thing, hydrogen has one electron as a valence electron. It only has one electron. So when it shares with another hydrogen, it actually achieves a noble gas configuration. And so the nearest noble gas for hydrogen, of course, is helium, which only has two electrons. So just like 8 electrons was perfect for all the other elements to get a noble gas configuration, for hydrogen, hydrogen only wants 2 electrons, and it is at a very stable place when it has 2. But what if hydrogen bonds to something that is very electronegative? Fluorine is the most electronegative element on the periodic table. And as a result of that, this electron tends to go toward the fluorine more. It's kind of like sharing with your big brother or sister. Whenever I shared with my big brother or sister, there was some unequal sharing that went on. So for hydrogen, it is getting ripped off. Most of the electrons that are being shared are closer to the fluorine because fluorine is so electronegative. So hydrogen takes on a partial positive charge. This is a Greek letter delta, the lowercase symbol for delta. And we say that hydrogen has a partially positive charge and fluorine has a partially negative charge. That's unequal sharing. So we're going to take a look down below here at some illustrations of this. A illustrates a pure covalent bond, such as we had talked about between hydrogen and hydrogen. And that is perfect sharing, 50-50. Everybody is treated equally. So the electrons actually spend most of their time right here, and that's why you can see the bulk of the volume are in between the two. Yes, they spend a little bit of time out there too, but the bond is really an electron cloud, shall we say, that's shared between the two atoms. If we look at polar covalent, and we can just use the word polar eventually, but we'll put all the words here. Polar covalent is unequal sharing. And if we used our hydrogen fluoride molecule as the example, this would be like the fluorine, this would be like the hydrogen, and you see all the electrons in the cloud tend to be over by the fluorine side. So this side is partially negative, and the hydrogen ends up being partially positive. This does play an important role in how these molecules behave. Finally, this last picture here demonstrates ionic bonding. And so in ionic bonding, this one has gained an electron, and this gave up an electron. And that's why you can see this positive charge for that one has occurred, and this atom over here took the negative charge. That is a case of ionic bonding. So A illustrates electron sharing, which doesn't happen, but there is unequal sharing, and that forms what we call a polar covalent bond. And a polar covalent bond is simply unequal sharing. So before we move on, let's just take another look at that. The bonding types that we have are either ionic bonding or covalent bonding. And under covalent bonding, we have pure covalent, and we have what is known as polar covalent. And that's where we're going to launch from. Ionic bonding, we're not going to touch too much on. Most of our time is going to be spent doing covalent bonding. So Lewis dot structures are most useful for covalent bonding. They can illustrate a little bit of ionic bonding, but ionic bonding is fairly simple. Covalent bonding is a little trickier. So we're going to draw the Lewis dot structure for H2. And hydrogen, one valence electron, another hydrogen, valence electron. And when they form a bond in between them, we indicate that with a solid line. So what's happening with the electrons? They are being shared. And this forms a pure covalent bond. And then that's a bond in which two or more atoms share one or more pairs of electrons. The driving force between covalent bonding is the octet rule. And the octet rule simply means elements combine to have 8 valence electrons. Except, of course, for hydrogen, which only wants 2. So unshared pairs of electron are pairs of electron that do not participate in the chemical bond. So when I draw, say, fluorine connected to fluorine, they each have 7 valence electrons, but they're sharing one pair of electrons in between them. So these outer electrons are called unbonded pairs or lone pairs of electrons. They are not participating in the bond. We also have things that are called double bonds, and oxygen is an example of that, and we'll figure out how to make these and know why they occur this way. But a double bond means that there are 2 pairs of electrons. So if you have 2 pairs of shoes, how many shoes you would have? 4. And so 2 pairs of electrons are simply 4 electrons. So beyond just double bonds, and those are 2 pairs of electrons that are shared between the molecules. Okay? There is such a thing as a triple bond, and that occurs in the nitrogen molecule. And the nitrogen molecule looks like that. And there are 3 shared pairs of electrons. So these shared pairs of electrons that comes out to equal 6 electrons that are shared between the 2. So we're going to talk about how to make these little dot and line structures that actually tell us what kind of bonding is going on between the molecules. And here are the rules. We want to add up the total of all the valence electrons for each atom in the molecule. And we write the symbols for the atoms in the molecule, And in a simple molecule, one atom will be the central atom, and it is going to be surrounded by all the other atoms. The central atom is often the first atom in the formula. Hydrogen can form only one covalent bond. In other words, it can only have 2 electrons max. So it can never, ever be the central atom. Hydrogen will never, ever be the central atom. So when we have lined up our atoms, we're going to draw a line between each pair of atoms that is covalently bonded together. After we do that, we want to subtract from our total number of valence electrons that are involved in bonding. We subtract all of those bonded electrons, and we draw the lines in between them. Okay? I'm sorry. We draw the electron pairs that remain around the atoms. So we want to arrange the dots so that most atoms have 8 valence electrons, except of course for our friend hydrogen, which will have only 2 electrons. If there are not enough electrons to give the atoms a full octet, we're going to need, full octet meaning 8, we're going to need to shift some unbonded electrons as necessary, or change single bonds to double or triple bonds. And we want to verify that each atom has a noble gas structure, or 8 electrons around it. Ions have either more or fewer electrons than protons in them. So if we come across an ion, we're going to need to either add if it's a negative ion or subtract if it's a positive ion. So let me give you a quick example of some Lewis dot structures. Iodine is an halogen. So on the periodic table, I notice that it has 7 valence electrons. So since their formula says I2, my total number of valence electrons are 14 electrons. So what I do is I draw each atom in the molecule, and I place my 7 valence electrons around it. I'm being a little bit wise in regards to where I'm putting that single electron, because I know that there is going to be a bond in between those 2 iodines. So this is the Lewis dot structure for iodine. There's a single bond in between 2 iodines. There is 1 shared pair of electrons, and there are 6 lone pairs of electrons total for the molecule. Okay? Let's do hydrogen fluoride. Hydrogen is in column 1. It has a single valence electron. Fluorine is a halogen, and it has 7 valence electrons. So all told, there are 8 valence electrons. And we draw a line in between those 2 to indicate that it is a shared pair of electrons. It's in the bond. Hydrogen has 2 electrons. That's exactly what hydrogen wants. Fluorine, on the other hand, has a total of 8 valence electrons. 3 lone pairs and 1 bonded pair. That gives fluorine its 8, and that gives hydrogen its 2. That is exactly what each of them want, and so we have a good structure for our hydrogen fluoride molecule. Let's do sulfur with 2 oxygens. That's called sulfur dioxide. And then we're going to compare that to sulfur trioxide. This is going to get a little bit tricky, so let's pay close attention. Sulfur has 6 valence electrons. Oxygen also has 6 valence electrons. They're in the same column, so we would expect them to have the same exact number of valence electrons. So let's take a look at what the molecule would look like. We need to choose a central atom because we have more than 2 in this. So we're going to start out with sulfur in the middle, and there's going to be 2 oxygens. So I'm going to put 1 on each side. Now before I get going, I'm going to count up my total valence electrons. There's 2 oxygens, so that's 12, plus 6 for sulfur. That's a total of 18 electrons. Now whenever you're doing the Lewis dot structures, you always want to work in pencil because there will be some erasing that's going to occur. Initially, I'm going to draw a bond in between the sulfur and the oxygens. That means I have used up 4 electrons, 2 electrons for each bond. That gives me a total of 14 electrons remaining to place around. So my goal is to give everybody 8 electrons. So I'm going to start with the guys on the outside and make sure that they all have 8. So I've got 14 to use up, and now I've got 12, 10 left, 8 left, and that gives that oxygen 8. 6 left, 4 left, 2 left, all used up. So I'm going to count just to make sure I didn't make a mistake. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's all the electrons I have to use. So this oxygen has 8 electrons surrounding it. 2, 4, 6, 8. This oxygen has 8 electrons surrounding it. 2, 4, 6, 8. Sulfur has only 2, 4, 6. That is not good. That's not enough for sulfur. It needs to have 8 electrons around it. But I don't have any more to give to it. So the only way that I can do it is to share another pair. So this is what I'm going to do. I'm going to begin, sorry about that. I'm going to begin sharing electrons between the atoms in the molecule here. And I'm going to erase this pair down at the bottom and share it in between there. I've created a double bond. So now let's do our math once again. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. This oxygen that has the double bond on it has 8 electrons around it. 2, 4, 6, 8. The sulfur in the middle has 8 electrons around it. 2, 4, 6, 8. And the oxygen on the left-hand side of the sulfur, 2, 4, 6, 8 with the single bond. So the correct Lewis dot structure for sulfur dioxide is going to look like this. There's a lone pair on the sulfur in the middle. There's a double bonded oxygen, and there is a single bonded oxygen. And we created a successful structure. All right, let's go to sulfur trioxide now. And sulfur trioxide is going to have sulfur in the, let's do our valence electrons first. So sulfur is equal to 6, oxygen is equal to 6, but I have 3 oxygens. So 18 plus 6, I've got a total of 24 electrons to place around. Once again, be working in pencil so that you can erase. And I'm going to do sulfur in the middle once again. Choose it as the central atom and place the 3 oxygens bonded around it. And so now I've got 18 electrons still to place. Each bond is 2 electrons. There are 3 bonds. So 3 times 2 is 6 from 24 leaves me 18. So 18 with 3 oxygens makes me think, oh, that's good because I can put 6 around each of them and give them each 8 electrons. And as I do this, I realize that all of the oxygens will have 8 electrons around it, but sulfur in the middle only has 6 around it. So let's take a look at that and say, okay, that has got to be fixed. 2, 4, 6 is not enough electrons for that sulfur in the middle. So in order to verify that I'm doing the right thing, I am going to do a quick check and make sure that I have the right number of electrons, make sure I didn't make any mistakes. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yep, that's the number of electrons I'm supposed to have. So in order to give sulfur in the middle enough electrons, I'm going to take this pair of electrons and that oxygen. And why did I choose that oxygen? No reason. I just chose one of the oxygens. They're all equal to each other. And what I'm going to do is I'm going to take that pair of electrons that I erased and share that pair to create a double bond in between the sulfur and the other oxygens. So what I would like you to do at this point in time is to do for carbon dioxide what I have done for the above. And then this is called carbonate, CO3 with a -2 charge. So when you add up the valence electrons for one carbon, which is 4, and you have oxygen, which is equal to 6, and I have 3 oxygens, I'm also going to have to account for that negative charge. Oxygen, carbon are all taken care of, but the negative charge means that the -2 that I have to now add 2 electrons to the total. That means there's 2 extra electrons in this structure. So let me count up my total valence electrons for carbonate. 4 plus 18, 6 times 3 is 18, so 4 plus 18 is 22, plus 2 electrons. There are 24 electrons total in this molecule. In each case, carbon will be the central atom. So go ahead and determine your valence electrons for carbon dioxide and then draw your structure for carbonate ion right here, and we'll check that when we get to class.